Welcome to the second recitation of fluid mechanics. This week we are going to have 5 different questions and we are going to get started with 3.43. So here we can see a manometer, and in this question we are required to find pressure at point A, which is here. And we can assign a random letter or symbol to this point, which is the final point or start point. So let's say this point is P. So in manometer questions, the easiest way is writing this equation. So this means that when we are going up, we will have negative pressure, and when we are going down, we will have positive. So actually, it doesn't matter where we are starting from. It can be either from B or it can be from A. So considering this selected point, we will have up or down. So let's say we are starting from B, because eventually we want to find PA, so that we can write PA as on the other side of the equation. So let's say we have PB, and now we are going down. So since we are going down, we will have positive value. And here we need to find the pressure of that water section. So specific weight is 9,810 Newton cubic meter times the height, which is 0.9 meter. And then we are going to the next one. Here we can take this point, because we don't need to calculate for these 30 centimeter sections separately. Instead, we can calculate pressure from this section, from this line to this line. And after that, we are going to skip to this section, so that we will have same pressure at this point and at this point, so that we are actually not required to calculate pressure at this section. So let's write the equation for mercury. Since it is still down from this point to this point, we will have positive. So to find the specific weight, if you remember, we have a relationship between specific gravity and specific weight. So specific gravity of mercury is equal to specific weight of mercury over specific weight of water. So to find the specific weight of mercury, we can multiply this value with specific weight of water. So here in the question, we can assume that the specific weight of mercury is 133.0 Newton over cubic meter. So let's use this specific weight here. And the distance is 0.6 meters. And now, as I mentioned, we are just skipping from this line to this line, because there will be same pressure at this point. And now we can start from this line up to this line. So we are following the same approach. Since there will be same pressure at this horizontal line, we don't need to calculate this pressure, so that we can just find the value from here to here. And this time you should pay attention that this is actually oil. So we are going to write equation for the oil. So let's write minus, because we will be going up, and we have specific weight of oil times we have 150 centimeter plus another 30 centimeter here, which means we have 1.8 meter of oil. And to find this, we can do this calculation. Sorry, it's here. Similar to mercury, we can calculate specific weight of oil. So it will be specific gravity of oil, which is 0.8 times the specific weight of water. And this is going to give the specific weight of oil. So we calculated the pressures in this section, and as I mentioned, we have the same pressure here until here because they are at the same horizontal level. And after that point, the only remaining part is from this line to this line, which is 1.5 meter section. And again, you should pay attention that we are actually going down here, so it will be positive again. And it states that it is water, so we have specific weight of water times 1.5. And since we are ending our calculations at this point, they will be all equal to PA, which is the pressure at point A. So here the only unknown is the pressure at point B. So if the question doesn't say there's an absolute pressure at this point, we can assume that pressure is 0 because this is open to atmosphere, and we can assume that the pressure is 0. So that, let's say this is 0. And finally, from here we can get PA. When you do all these calculations, we can get 89.2 kilopascal pressure. Okay, let's continue with second question. This is question 3.47. Again, in this question, we have a manometer. This time, these manometers are not directly connected to each other. As we can see, they are both connected to this air tank. And in the question, we are required to find the deflection, difference in deflection between this height and this height. Or in other words, we need to find delta HA, which is this section, and delta HB. But still, I want to read the question. We have two other manometers are connected to a tank of air. One leg of manometer is open to 100 kilopascal pressure, which is absolute, while other leg is subjected to 90 kilopascal, which is here. And we need to find the difference in deflection between both manometers, or delta HA minus delta HB. So as we did in the previous question, we just need to write this calculation, which is if you are going up, we will get minus, and if it is down, we will get positive pressure value. Let me change the color. So we can think first this leg. Let's say we will start from here. We have 0.9 atmospheric pressure. And also, if you remember in the previous question, we were assuming pressure is 0 if they are open to atmosphere, but this time absolute pressures are given, so that we need to stick with these values. So we have 0.9, and this pressure is affecting until this line, and after this line we have water. So the pressure will be same at this point and at this point, so that we can just discard this here, this pressure, and we can just calculate this side. So the water column is delta HA, and since we are going up, we will get minus specific weight of water times delta HA, and this is equal to PT. On the other hand, we have this right leg with 100 kilopascal. Again, similarly, we will start with PATM. We are going down and we are coming here. Until that point, we don't have any fluid, so we can just stick to this value. Then we are skipping to this leg, since we will have same pressure at this point. And then we have this water height, which is delta HB. And since we are going up, again we will have delta W times delta HB. And similarly, this is also equal to PT. So we have two equations here. And if you can use these equations together, we will get delta H minus delta HB. So let's make a simplification. The left leg is equal to right leg. Sorry. And here we have same values. This is 1, this is 0.9, and we have 0.1 PATM equal to delta V, delta W, and this is going to be positive because we are moving this from left to right, minus delta HB. And we can leave this value alone. If you do that, we will get delta HA minus delta HB is equal to 0.1 PATM over specific weight of water. And PATM is 10 to the power of 5 Pascal. And we have specific weight of water. And from here we can get this value as 1.02 meters. So this gives the deflection difference in these manometers. Okay guys, let's continue with question 3, which is 3.58. Here we have a hydrostatic force question. And let me read the question first. As shown, a round weaving window of diameter 0.8 meter is situated in a large tank of seawater, which is here. And the specific rate of seawater is 1.03. And the top of the window is 2 meters below the water surface. So we have H as 2 meters. And the window is angled at 60 degrees with respect to horizontal. And we need to find the hydrostatic force acting on this window. And we need to find and locate the corresponding center of pressure. So in this question we are required to find two values. The first one is hydrostatic force, which is kilonewton, and the other one will be center of pressure. Okay. So first of all, we need to find distances using trigonometry, and then we need to find the pressure at the depth of center of this window. Then we are going to find the resultant force, which will be PA, and P average pressure times area. And we need to find the distance between the centroid and center of pressure. And to do that, we will use this equation, which is the height of center of pressure minus centroid is equal to inertia over centroid times area. Okay, so first of all, let's find slant height. So this is actually centroid of this window. So here, since we have a slant here, we cannot directly find this height as depth of the centroid, but later we are going to calculate depth of centroid as well. So for this one, we need to find the height from the centroid to the water surface. So we need that slant height. So it will be the centroid of window. So here, first of all, we have this half of diameter. So we have radius as 0.4. So let's say d over 2, or we can say 0.4 meters. And then we need this distance, and for that we need to use trigonometry, and here it will be 2 meters over sinus 60. And from that we can get 2.709 meters. So if it wasn't clear enough, we can do something like this. So this section is 0.4 meters. I mean, this is the window, and its diameter is 0.8 meters, and we have 0.4 meter here. And then we need to find this distance. So basically you can draw something like this. So this is 2 meters, and we have angle as 60 degree. So for example, if we take this angle as sinus 60 will be equal to, we have this opposite over hypotenuse, let's say x, 2 over x, and x will be the slant height of our window. I mean, it is slant height from the top of window to the surface. So here x is equal to 2 over sinus 60. And as you can see, we have 2 over sinus 60, and we have 0.4. In total, let me use another color. In total, the distance from center of window, so centroid of window to top of water. I'm not sure if it is visible, but it is the distance from centroid of water window to the top of water or surface of water. Okay. So the next one we are going to calculate is, and actually we already calculated this value, which is slant height, and now we will get depth of centroid. This is required because To calculate pressure here, we are required to find specific weight times depth of centroid. So we can use this equation. Let's say delta z or delta z. So this time we will get depth. This is not height, this is depth of centroid. So let's draw this line, and we are required to find this depth. And we already have 2 meters from here, from the water surface to the top of window. And then we have this small distance, again, which will be let me use this one. This time it will be this distance, and you can think a triangle like this. We have 0.4, we have 60, and we need to find this, which will be this distance from the centroid. So it will give the remaining part of this depth. So we will have h, which is 2 meters, plus d over 2 sinus 60. Or we can say 2 plus 0.4 sinus 60, and this is equal to 2.346 meters. And here we can do sinus 60 is equal to y over 0.4. So basically this depth will be equal to 0.4 times sinus 60. Okay, now we can skip to calculating hydrostatic pressure, which means we have P, and P is equal to, as you know, specific weight and depth. So it is equal to specific weight times delta Z. Specific weight is given, yes, since we know the specific gravity, we can calculate the specific weight of seawater. So you can do that. I will directly write the final specific weight. So the specific weight and delta Z is here, 2.346. Yes, and this is equal to 23.7 kilopascal. And now we can finally get the hydrostatic force, which is F is equal to P, which is hydrostatic pressure, times area. And we will directly write P. And the area is area of this gate. Actually, let me draw these lines. So this is the gate, and we need to find its area. And also in the question, we said that we have a round window, so that we need to use equations for circles. So area will be pi times r square. So we will get 11.9 kilonewton. So this means that we have a hydrostatic force, but we actually don't know where is the center of pressure. It can be either here, it can be here. So to calculate that, we will benefit from this equation, which shows the distance between the center of pressure and centroid. And let me write here. We have center of pressure minus y bar. Yes, it is 2.010.709, and this is equal to inertia, and you can find it from figure A1. And we will use inertia equation for circles. So it is P so we have pi 0.4 meters to the power of 4 over 4. And this gives 0.01476 meters. We can get center of pressure minus centroid is equal to 14.8 millimeters. Is it visible? Yes. So what does this mean? Let me use white one. So here we calculated the centroid, and its height from water surface is 2.7. This is 2.709, and the final result says that the difference between the center of pressure and the centroid is 14.8 millimeters. In other words, we have the centroid, and center of pressure probably will be here. Of course, it should be much smaller than that, but we can say it is here. So the correct center of pressure almost here. So let me write YCP. And actually I want to make this gate clear, so that it will be more visible. So briefly, we have this gate, we have this centroid, and again we have this YCP, which is center of pressure, and the force is acting here, and this distance is 14.8 millimeters. this is question 4 and this is 3.59. First, let me read the question. We need to find the force of the gate, which is gate, this one, on the block. The block is here. And D is 12 meters. So this is 12 meters. H is 6 meters. And the width is also 6 meters. So here, this time, we have a different gate. The gate in previous question was round, so we did all calculations considering circle, like area of circle, inertia of circle. But this time we have this type of gate, 6 to 6. And therefore we are going to use rectangular inertia. So let's get started. Since again we need to find the force of gate on block, first we need to find hydrostatic pressure and hydrostatic force. So if you remember, F is equal to pressure times area. Or in other words, we can say pressure was equal to specific weight times depth of centroid, let's say y bar, times area of this gate. And so this question is actually easier than the previous one because we don't have slant height, we just have this centroid. So we can directly get the centroid depth, which is 12 meters from water surface to the centroid. So this is 12 meters. And specific weight is given this is of course Newton over cubic meter. And the area will be 6 times 6. And from there we can get 4.238 to the power of 6 Newton. Okay, so we calculated the hydrostatic force on this gate, but still we don't know the center of pressure as we did in the previous question. So it can be either here, it can be here, here. So we need to find using the same equation. Slant height is, we don't actually have slant height, so we are using depth of centroid. So you can either say this is depth of centroid or it will be equal to slant height because it is already a vertical line, a vertical distance. So that it is either y bar or d. So again, from figure A1 you can get inertia equation for rectangular. So this is equal to y bar times a, and we actually have b times cubic h over 12 is inertia, and from here we can get ycp minus y is equal to 6 times 6 cubic 6 12 over, we have 12 for the depth of centroid times 6 and 6, which is the area of this gate, and from here this distance will be 0.25. So in other words, we can say that, let me use white. So this is the centroid, and the center of pressure, let's say it is here, and this distance is 0.25, and this is YCP. Okay, so this means that we have force acting at this point. So in the question it says that we need to find force of gate on block. So we need to use equilibrium so that we have pivot point here, and we can sum moments on this pivot. So let's start with the force. The force was calculated as this value. So F hydrostatic pressure times center pressure minus Y bar. So this means that we are calculating momentum of this force of gate. The value of force times this distance to the pivot. So this is 0.25, and this is 4.238 Newton. So this is equal to, so we have force from left to the right, and we will get the force of block. So it will be from right to left. So if you take this as reference, this will be positive, this will be negative. So now from right to left, we have force of block times the distance from the block to the pivot. So we can take this level. So this is actually 3. So this means that from the bottom of block to the centroid we have 3 meters of distance. So we can calculate momentum at pivot. This is going to give us F block as 353, so 353 kilonewton. Okay, so I thought there was a confusion here earlier. So since there's no inclined gate like the previous question, but since we have this vertical gate, we don't actually calculate slant height. So you can either use Y bar or we can just use D here. So it is going to give depth of centroid, and then we can do calculations. Okay, we are getting closer to the end. So this is question 5, and it is 3.65 in your textbook. So first, let me explain the question. Here we have this butterfly valve here, and we are using this to control the flow in this 12 feet diameter outlet pipe in a dam. So this is a dam, and it is holding this water behind of it, and this gate is used to control the flow in this pipe. And the diameter of the pipe is 12 feet, and the diameter of the shaft, the diameter of the gate is also 12 feet. In the position shown, the valve is closed, and the valve is supported by a horizontal shaft through its center. So we have a shaft here. The shaft is located at H. It is 60 feet in the question. Below the water surface, and we need to find the torque would have to be applied to the shaft to hold the valve in the position shown. So briefly, we need to find the torque required to hold valve in this position, and to find that we need to find the hydrostatic pressure, then hydrostatic force, and finally we need to find the momentum at the shaft so that we can hold that in that position. So let's get started. So as I mentioned, we need to find hydrostatic force. In other words, it was depth of centroid specific weight times area. So here, to find the hydrostatic pressure, first we need depth of centroid. So it will be the depth from the water surface to the center of this gate times specific weight times area. So depth is 60 feet as given here, and we have specific weight as 62.4 pound over cubic feet, times we have area of the gate, and a butterfly valve is a circle gate, so it will have area as pi times r square. So from here we can get hydrostatic force as 4 to 3 and 4 to 6 pound force. So it is 400,000 and 436. And now again we calculated the hydrostatic force, but we don't know the center of pressure of this force, and we actually need to find that because in the question it says that we need to find the required torque that is going to hold this shaft in this position, so that we know that there's a force from here, hydrostatic force, and since the shaft is at the centroid, this force times this distance will give the torque. So when we have this force, it will hold the shaft in this position. So as we did in previous questions, we have the center of pressure minus slant height is equal to inertia of circle over depth of centroid times area. So from figure A1 in your textbook, you can see this value for inertia for circle. And when we write that, it will be pi times 6 to the power of 4 over 4, and the area is pi r square. And the only unknown for now is y bar, which is slant height. So since this gate is inclined, we need to find slant height instead of directly using depth of centroid. So in other words, we need the distance from this centroid to the water surface, I mean in this slant height. So again, using trigonometry, we can just calculate this distance from centroid to the here, because we will have 60 here. So y bar, or this distance, will be equal to 60 over sine 60. And if we substitute this value in this equation here, so it will be equal to pressure of center of pressure minus slant height, which is 60 over 0.866, is equal to 6 square feet over 4 over 6 feet divided by 0.866. And this is actually a simplification of this equation, because we have pi, we have r square, and we have other common values, so that the distance between center of pressure and centroid will be equal to 0.1299 feet. So, and to find the torque that is required to hold this valve in this position, we need to find force acting on this gate times distance between the center of pressure and centroid. So since we calculated as 0.1299, so this distance is actually this distance between the center of pressure and centroid. So we have this hydrostatic force. So torque will be equal to force times distance between centroid and center of pressure. And finally, if we apply a torque of 55,000, we can hold this value in this position.